Hello kiddos and welcome to the Law of Combining Volumes. So very important in today's lesson is that you brush up on your balancing equations because that's going to be super helpful with learning how to do this. There's no formula per se. There's just a concept of how we think about gases, and it works with balanced equations having to do with gases. So let's take a look at our objectives for today. We're going to describe and compare the behavior of real and ideal gases in terms of kinetic molecular theory. And we're also going to explain the law of combining volumes. And really important that we look at, for today, the kinetic molecular theory. Okay, kinetic meaning movement of particles. Molecular is um, things like molecular compounds, right? Nonmetals plus nonmetals or gases. And these are just theories, remember? It's not a law, it's just a theory, but we're definitely going to talk about that. So some background information. So the central idea of the kinetic molecular theory is that these particles, these smaller particles, or any particles such as atoms or molecules or ions are constantly moving. There's this constant motion. And this motion, very often, is described as continuous and random, okay? And oftentimes, they're more, they're depending on if you're in a solid, liquid, or gas, the movement is going to change. For example, in a solid, it's just vibrational movement. In a liquid, you have a little bit more movement. But with gases, you have very random, continuous movement. This is known as Brownian motion. You don't really need to know that word, but just so you know, some background info. So according to the kinetic molecular theory, the motion of molecules is different in solids, liquids, and gases. So remember, in solids, it's just basically vibrational movement. In liquids, it's vibrational, but it's also rotational and some translational. What translational means is diagonal. Okay, so there's lots of this type of movement. Here we just have a vibration, but in gases, we have all kinds of movement. We have translational mostly, and it's very random, but it's continuous. Okay, it's very continuous, which means it just doesn't stop. And recall, with gases, you have a lot of spaces here. That's why they're easily compressible. Liquids, they're not so compressible at all, and with solids, it's zero. With liquids, very, very, very little. The only thing we really kind of attribute compression with are gases. So the kinetic molecular theory explains a few things. It explains why gases are compressible, and it has to do with a lot of space. You have a lot of unoccupied area, and these particles are constantly moving. So when you decrease the volume, okay, you're actually squishing them closer together, but they're still vibrational movement. It explains gas pressure. So remember, with pressure having to do with gases, it's talking about the collisions over the walls of a container, okay? And the more collisions you have, the higher the collisions you have, the higher the number of collisions you have, we contribute that to a higher pressure. And also Boyle's law. Due to reduced volume, there is shorter distance between walls, thus more frequent collisions causing an increased pressure. So whenever you're talking about kinetic molecular theory, you have to talk about the movement of a particle, and you have to talk about how that movement influences things, whether it's pressure or compressibility, that kind of thing. And finally, Charles' law, due to the increase in temperature, there is an increase in particle speed causing more collisions with the wall. The wall moves outward, thus the volume increases. Another thing to keep in mind with the kinetic molecular theory is the space between the particles. Is the space increasing or is the space decreasing? Okay, so now we're talking about the law of combining volumes. Now, the law of combining volumes you kind of deal with it from two perspectives. The Avogadro perspective, you know Avogadro, he came up with the 6.02 times 10 to the 23 particles in a mole, and the Gay-Lussac perspective. So these two guys had a different perspective on how gases behave, and then they're like, hey, let's take all that you learn and come bring it together. So the kinetic molecular theory explains why many physical properties of gases are what they are. But it doesn't really go into the chemical properties. In 1809, however, Joseph Gay-Lussac, who is a colleague of Jacques Charles. Now, these people all kind of work together, and they all bounced these ideas off each other, and they all kind of went, oh, Charles, that's your law. I'm going to kind of take that law and kind of add to it. So what he did, though, Gay-Lussac, is he measured the relative volumes of gases involved in chemical reactions. His idea was taking a look at the volume of gases. That becomes very important. And his observations led to the idea of this law of combining volumes. And what it states, and I'm going to read it word for word, when measured at the same temperature and pressure, so temperature and pressure has to be constant, because you know that temperature and pressure both affect volume, so that has to be constant. So when measured at the same temperature and pressure, volumes of gaseous reactants and products of chemical reactions are always in simple ratios of whole numbers. Okay, really important, ratios and whole numbers. That becomes really important. And this only happens when you're talking about gases. This concept doesn't work with liquids or solids. Okay, so where do we get these whole numbers, and how do we look at these ratios? That's what we're going to look at right now. So he came up with a simple example. And we're going to take a look at how this example, I need you to just basically be open to the fact that these numbers here, these coefficients, mean a lot. Yeah, we get them from balancing our equation, but what do they actually mean? Okay, so when we're looking at water and breaking it down, or, you know, through hydrolysis, it's going to break down into hydrogen and oxygen. When we do that, we have to balance the equation, correct? So we have to make sure that the hydrogens and the oxygens on the reactant side equal the hydrogens and the oxygens on the product side. So we go ahead and balance the equation. After we balance the equation, we get this 2 to 2 to 1 ratio, okay? What that means is the amount of water and gas and hydrogen is always going to be equal, because it's a 2 to 2 ratio. Do you see that? It's 2 to 2. Oxygen, however, I'm always going to have half the amount of oxygen when compared to hydrogen and when compared to water. So when I'm comparing water to hydrogen, it's a 2 to 1 ratio. When I'm comparing oxygen, same ratio with oxygen to water and oxygen to hydrogen. It's both 2 to 1. Okay, that ratio becomes very, very important, that concept. So 2 years after Gay-Lussac's law, Avogadro proposed a new explanation in terms of numbers of molecules. So what Avogadro proposed was equal volumes of gases. So now he's like, wait a minute, it's not just the numbers, it's not just the 2 to 1 ratio. How about we link that to volume? So equal volumes of gases at the same temperature and pressure contain equal number of molecules. That's what's key here. He's saying no matter what, if I have 1 liter of any gas, it's going to contain the exact same number of molecules. That's really important. So from that thinking, right, we're looking at the mole ratios provided by a balanced equation are also the volume ratios. So the mole ratios, which means those coefficients like 2 to 2 to 1, mole ratios and volume ratios, we can see them as the same. Okay, and this is known as Avogadro's theory. So let's take a look here at another example. When all gases are at the same temperature and pressure, the law of combining volumes provides an efficient way of predicting the volumes of gases in a chemical reaction. So let's take a look at the example here. We have nitrogen plus hydrogen gives you ammonia gas. Notice that they're all gases. So if they're all gases, we can use the concept of the law of combining volumes to say, listen, there is a profound ratio. It's a 1 to 3 to 2 ratio. So here are my coefficients, 1, 3, 2. I can see that 1, 3, 2 as in 1 moles, 3 moles, and 2 moles. But for gases, I can always also look at it as volume. 1 liter and 3 liters and 2 liters. I can also take a look at volume in terms of milliliters. It's a 2 milliliter to 6 milliliter to 4 milliliter. Let's take a look at that. What just happened there? Well, if I don't have 1 liter of nitrogen, let's just say I have 2 milliliters of nitrogen, I'm going to treat these with the same ratio. 2 times 3 is 6, and 2 times 2 is 4. So it's this ratio that continues on. Okay, use the volume. So now we're going to take a look at some examples. Use the law of combining volumes to predict the volume of oxygen required to complete the combustion of 120 milliliters of butane gas from a lighter. Okay, cool. So you're going to, first of all, write out your equation. I have butane plus oxygen yields carbon dioxide plus water because it has to do with hydrocarbon combustion, right? And because it says here, complete combustion. And we know we're dealing with oxygen and butane. Where is it? And butane gas. So here's our butane. Here's our oxygen. You know that the two products are always carbon dioxide and water. So once I balance the equation, I have a 2, 13, 8, and 10. Those are my coefficients, and those are what's going to help me organize my life, really. So we want to figure out how these coefficients relate to each other. So the first step is to write down the balanced equation. And then from this chemical equation, you can see that 13 moles of oxygen is required for every 2 moles of butane. Therefore, we come up with this kind of ratio here, where it's a 13 moles or milliliters, same as moles of oxygen for every coefficient of 2 of butane. So this is our ratio here, kiddos, and that comes from a balanced equation. I always start my my equation with what I'm given. Okay, I am given 120 milliliters of butane, and if I want to find out how many milliliters of oxygen I have, I use my ratio to help me figure that out. Now remember, why do I have butane here? Because I have butane here and I want to be able to cross them out. So what you have always goes on the bottom, and what you're looking for is always on the top. It's always the numerator, okay? And you always start your equation with what you're given. This is what you're given. And I like to write down the species so that it keeps my thinking organized. So once I do this, I'm going to just erase this so I can show you. All I'm really doing, taking 120, multiplying it by 13, and then dividing it by 2. Okay? I'm multiplying it by 13 and then dividing it by 2, and I get my answer of 780 milliliters. To make sure that the ratio is used in the correct order, you could include the chemical formula with each quantity as shown above. Note the cancellation of units in chemical formulas. So that's just to kind of keep you grounded. Okay, here's another example. A catalytic converter in the exhaust system of a car uses oxygen from the air to convert carbon monoxide to carbon dioxide. So I'm converting carbon monoxide with oxygen to carbon dioxide, which is released through the tailpipe. If we assume the same temperature pressure, obviously, what volume of oxygen is required to react with 125 liters of carbon monoxide during a 100-kilometer trip? Okay, that makes no difference, so we're not even going to look at that. So we're going to balance our equation, right? So I have carbon monoxide plus oxygen yields carbon dioxide. Or I'm gonna go ahead and balance it. It's a 2 to 1 to 2 ratio. Also, something that you want to do is you want to populate your balanced equation. I have 125 liters, and I'm looking for the volume of oxygen. If my volume is in liters, kiddos, this answer is also going to be in liters. So now, remember what you do is you start with what you have, what you're given, 125 liters of carbon monoxide, and I'm going to use my ratio from the balanced equation. Okay, I'm comparing carbon monoxide to oxygen. This is what you have, and here is what you want, or what you're looking for. And these numbers, again, come from the balanced equation. I'm only concerned with these two. Okay, this goes here, and what I want is on the top. I'm not concerned with that because that's not what I'm looking for at all. So now, once I've figured that out, once I set this up nicely, I know that my carbon monoxides are going to cancel out. So really, I'm just going to go 125 times 1 divided by 2, which is going to give me 62.5 liters of oxygen. All right, kiddos, so once you balance your equation, you come up with those coefficients, you can definitely do this very easily. According to the law of combining volumes, 62.5 liters of oxygen is required. So this equivalence between the chemical amounts, or the coefficients from balancing, right, and the volumes only works for gases and only if they are at the same temperature and pressure. Here's some extra practice, and there's some in your note package, so go ahead and get that done.